everybody knows SpaceX at this point. If you don't, you live in a cave. Elon Musk of PayPal fame and Tesla fame basically decided to make tons of money so that he could make a rocket company to go colonize Mars within his lifetime. I mean, literally, that is his goal. So some people think that's crazy. Other people think it's attainable. This goal of becoming multiplanetary has been in our collective consciousness since many generations. And it's become a sci-fi concept as well as a reality at some level. So today we're going to just talk about the reality of colonizing another planet and why we pick Mars. Mars is the closest in size to Earth, and that becomes important. And also it's got what could become an atmosphere if you terraformed it. So it's just the best in terms of effort for colonization. First thing about colonizing Mars is you got to get there. And at this point in time with our technology, it's not particularly a short trip. So there's two periods of time when Mars is in the right configuration with Earth that you can travel to Mars without spending tons and tons of energy. And what I mean by energy is that every planet in the solar system, and we talked about this a little bit before, has mass. And the amount of mass you have in one spot, that determines its gravitational potential. The gravitational potential is the representation of the energy that you need to overcome to land on or escape from that body. So the planets have mass, the sun has mass. So you can think of these things right here. It's just showing the sun and Mars at two different periods of time. So here is for this short stay. Short stay means you land on Mars, you stay for a little while, and then you take off again and come back to Earth. So this means your total mission time is the shortest. So this is basically the shortest mission we could currently do to get to Mars and get back to Earth. So if you look at this, the outbound leg, when you take off from Earth right here, and you fly in your spaceship and you come into Mars orbit, and then you arrive on Mars, that takes 313 days. And then you get to stay on Mars for a month. You take off, and you actually retrograde around the sun and use the sun's gravity to get you back to Earth. And that takes 308 days. So this path is actually a little bit farther than this path, but both of these things you can imagine you're going to be stuck in your spaceship for almost a year. Now there's the long stay or conjunction clash. So this makes a lot more sense in terms of how long you have to stay in the spacecraft, which becomes important a little bit longer later on in the lecture. Your outbound trip is 180 days, and it's a pretty short hop. And you wait till Mars goes all the way around, so you almost spend a full Martian year, and then you take off again, and you come back, and you'll land back on Earth. So these two opportunities with our current technology allow for different mission profiles. Both of them mean that you're going to be not on Earth for almost multiple years. Not many chances. So here's a chart showing all of the possibilities. Well, I got this chart a bit ago, so we can skip through from 2012. Clearly, we've missed those opportunities. You can see that October of this year, this was one of the ones SpaceX wanted to use about a decade ago. They said, we're going to launch October 13th, 2020. Clearly, that's not going to happen. So your next available opportunity really is in 2022, and that's something that Elon Musk has actually proposed in a recent article and talk he's given. He's like, they want to have their Starship sending at least supplies to Mars by this time frame, which, whether you think that's optimistic or not is up for debate, and we can get to that debate a little later. But this is just to demonstrate that, yes, there is basically, you can see on average, about 26 months in between opportunities to go to Mars, depending on which of the previous two types of mission profiles you're going to have. So you can see that this period right here is around 26 months. So we don't have a lot of chances to go to Mars. So when we have that chance, we need to be ready to go with a lot of different pieces of material. If we really want to colonize Mars, you get this chance every 2 years. You need to send a lot of stuff then, because you can't really do it in between. Now you can get to Mars in between, but you're going to expend a lot more energy. You're going to use a lot of energy to move your spacecraft and maneuver it in order to intercept the planet. So that's why we have not many chances. Okay, so given that you're going to be spending a lot of time in space, and then you're going to live on Mars, the biggest factor, besides just having a vessel that can actually do it and sustain life in space, is radiation. So we're going to talk a little bit about radiation and make sure everybody's super brainiacs. The SI units, which I'm sure you've all heard of, that's the Système International. Unfortunately, the French were first in science a couple centuries ago, so a lot of things dealing with standards are in French. They're not particularly as good this day and age in terms of the forefront of science, but we call them SI units, and you'll know that SI units are what's termed acceptable measures. So there's lots of different things we use to measure things. In America, we still use imperial units, gallons, pounds, miles. Those things are based on an old English system. The actual definition of those things, gallons, pounds, miles, is actually a conversion from acceptable SI units. In other words, kilograms, meters, seconds, times, stuff like that. So these are the accepted units for radiation. We have an absorbed dose, which is a gray. We have an equivalent dose, which is a sievert. And we have activity, which is a becquerel. So these three things are what's used to describe actual radiation environments and how that impacts with human or living matter. You'll probably be familiar with some of these non-SI units, which is RADs, REMs, and Curies. So Mary Curie was the first scientist to discover radioactive materials and describe them in a certain way. And she died of cancer because of exposure. But for a while, we named the activity after her. But these are the accepted units. So let's talk about what these units are. A becquerel, 1 nucleus decay per second. So that represents the amount of material that's decaying. Decaying means that you've got some type of solid that's made up of atoms, and those atoms aren't particularly stable. When atoms become too big and they're in the right sequence on the chemical chart, they don't stay stable. They just aren't in a stable quantum configuration. And that's what causes nuclear decay. So nucleus decay per second. That's not the only way to get radiation, but that's one of the ways that we get particulate radiation. We'll talk about all the different types of radiation in a little bit. So let's go on. The one we're really going to be interested in is the sievert. So a sievert, equivalent dose. So remember that. So we get the conversion from a gray to a sievert. So grays, as we saw it before, it represents absorbed dose, or how much radiation you've been exposed to, right? But that could be meaning a lot of different things. The types of radiation that are common are alpha particles, beta particles, neutrons, and rays. X-rays are detected here, but it could be gamma rays or X-rays. Both of those types actually in the high ultraviolet spectrum as well can cause actual damage. It's called ionization radiation. So any type of ionization radiation is able to impact your living tissues and cause damage. So with these 4 types of radiation, each one has a different impact on the body, right? It has a different amount of impact. So gamma ray or X-rays, which are shown here, they made the map from absorbed X-rays to impact on the body, a 1-to-1 map. So that's how they set the level of a sievert. A sievert is set on the impact of X-rays on the body and what kind of damage is done. So sievert represents how much radiation is going to cause how much damage. If you talk about beta particles, those also are similar in impact to X-rays. If you talk about alpha particles, those are 20 times more harmful to the body than beta particles or X-rays. And also neutrons, depending on their energetics, can be up to 20 times as more impactful. So you really don't want to be exposed to alpha radiation, but alpha radiation, because it's such a large molecule, really doesn't go very far. In fact, it won't go through the air very far. You could be standing next to a source of alpha particles and be pretty safe. However, if you ingest something or a particulate gets into your lungs, this is why if you are in a plutonium processing plant and you accidentally get plutonium dust in your lungs, it's almost 100% chance you're going to die of lung cancer. And then we have to look what types of, so I know it's getting a little bit complicated. We talked about this radiation weighting factor, which I think everybody can understand at this point. It's the amount of radiation you're exposed to and what type it is that becomes this radiation weighting factor. And then we got to go over here and talk about what kind of tissue is being radiated. So this is the tissue weighting factor. If your hand is exposed to radiation, well, your skin can be slightly sensitive to certain types of radiation, and your bone marrow can be and stuff like that. But it's nowhere near as sensitive to radiation as, let's say, your lungs, your gut, your intestines. Those tissues are much more sensitive to radiation. And in fact, at this point is where we talk about the first times that people were exposed to large levels of radiation and appeared to be okay, and then would die about 40 days later. That's because the tissue, the lining of your intestines, it replicates itself on about a weekly schedule, and it has 4 or 5 layers. It's much like your skin. And if it damages the DNA of the basal layers of the intestine, you can imagine that, unfortunately, about 4 weeks later, the intestine just completely fails. So a lot of types of radiation in the early days, when they're coming up with these types of ideas and things, were based on people getting overexposed and they die. It's called the LD50, the lethal dose 50, and they came up with levels of radiation that would impose a lethal dose, and it would be weighted on a time scale. So how long you got to live after you were exposed to that dose. Anyhow, I don't want to digress too far, and this is all the kind of math that comes up to us having this measure here. This is the measure that's important for us, especially in spaceflight or as pilots or as workers in a mine or a factory, or you work in a radiation, in a nuclear facility or something. This is the measure that you're interested in. It's called the sievert. And that's the one that tells us how much we're exposed to. Okay, life on Mars. Well, we're on Earth, and most places on Earth, you're exposed to about 2.4 millisieverts per year. Not bad. It's okay. We'll see on a chart in a little bit what that represents. This is mostly due to radon, radioactive potassium, radioactive carbon, gamma rays coming in. So you have background radiation. Depends on where you live on Earth. This could be higher or lower, but this is about it. the background radiation state for most people on the planet. You're exposed to around 2.5 millisieverts. If you worked in a nuclear power station, for the most part, you'd be exposed to about 10 times that. And then if you go up into the International Space Station, oof, now you're exposed to basically 2 times the level at which impact is most likely. The beginning level of impact in terms of millisieverts is about 100. And after this fact, people that have been exposed to this, their cancer levels are higher than the background population. So on the International Space Station, you definitely want to stay in a shielded environment. If you go into outer space, you're exposed to, in our solar system, 600 millisieverts. That's 3 times what you'd be exposed to on the International Space Station. Now, we talked about last time what is protecting people from this type of radiation, and that's the Van Allen belts, right? The Earth's magnetic field. So even though they're not in the atmosphere, they're in low Earth orbit, they're protected from 2/3 of the radiation that's actually hitting the planet, which is pretty good. The Earth is a great place to live. It's a nice planet. It does well to protect us. Okay, let's look at some of the radiation effects. When you're exposed to low levels of radiation, oops, this thing keeps popping up. Like, let's say the yearly limit for nuclear workers, there's no detectable increased risk of cancer. That doesn't mean that the type of radiation you were exposed to couldn't cause cancer. It just means that statistically over time, being exposed to 20 millisieverts is acceptable. It doesn't cause any detectable increase in the worker's health over a long period of time. You can see here that if you're a pilot, you're exposed to about 3 times the amount of radiation as someone who works on the ground. And that's well below the amount of radiation that you're exposed to if you worked in a nuclear power facility. So those 2 things kind of give a good context to the amount of radiation we're going to be talking about. And also, if you go get a full body CAT scan, you're exposed to a lot of radiation in one small period of time. So you don't really want to get a lot of CAT scans every year. You can imagine if you got 10 CAT scans per year, you'd end up at the risk of cancer level. So 100 millisieverts, we're up there. We have the level at which cancer can be noticed in populations that are exposed to this level of radiation. Then we go up to events. 400 millisieverts was the highest hourly radiation recorded at Fukushima. So if you were exposed to that for 4 hours, you might be expected to end up with radiation sickness. Once you hit 1,000 millisieverts, you have a quite high chance of cancer at that point. But this doesn't mean that you're going to die right away. 2 times that is when you start to see acute radiation sicknesses. At 5 times that, that's the LD50 level for a human. This is what we were talking about before. So if we have 5,000 millisieverts exposure, you can expect that you've ruined your intestinal tissues and you won't survive past about a month. 10,000 millisieverts, you've got actual structural damage to internal tissues. They're going to decay and not survive within days. A lot of this statistics was, unfortunately came about from accidents where people were exposed to, very high levels of radiation, especially Chernobyl. There's thousands of workers that were exposed to these levels of radiation. So it was unfortunate, but the statistics of their demise allowed us to have a much more accurate measure of radiation risk. And it goes through some of the things. Your eyes, you don't want to have exposure because you'll end up with cataracts. Thyroid's really bad to get hit. Young people are more at risk for that. DNA damage in the lungs, not a good thing to have. Stomach lining is the one that really gets bad. Your reproductive organs can become damaged. Can't have kids. Skin can become damaged, burning, slough off, bone marrow. Yep, all that fascinating stuff. Let's move on to another risk. So we covered the number one risk of this colonization idea is radiation effects. Number two risk is you weren't designed to live in space or on any other planet. You were designed to live on Earth. So on the ground on Earth, you're bipedal. You stand on your feet and you walk around. And your body has a system, lymphatic system, and a cardiovascular system that maintains the pressure inside of your vessel. You're like a little walking around, bag of fluids, and those fluids, if they weren't maintained in terms of their pressures, would all slump down and fill your feet, and you'd have an empty head. Some of us have empty heads anyhow, but I digress. When you're in space, the first thing that happens to you is you turn into this guy, like Stretch Man. All of the systems that keep the fluid under increased pressure in your feet and legs squeeze that fluid up into your torso and your head, and you become, you even could suffer from embolisms and fluid type damage. So this is not a fun place to be in. Your body will adjust. Obviously, astronauts have stayed in the International Space Station for many years, and they find out that they adjust to those microgravity environments. So all the people who are traveling currently on one of these spaceships that have been designed are going to end up like this when they land on Mars. And then once they land on Mars, you're going to have a return to a system that is not Earth. So we don't know exactly what a long-term exposure to reduced gravity is going to do. So there's no known study on partial gravity over long periods of time, what that's going to do. So it could be that this is actually detrimental to human survival, and our colonies might have to be on gigantic spinning tracks that rotate around in a great big facility that increase the gravity. It's not known yet. The longest people have stayed in microgravity is, long-term exposures over a year, but consecutive long-term exposure is more than that. And there are changes, even changes in the DNA to people being in microgravity. So we're going to have to figure this out. This isn't a trivial question. And especially when you're talking about how many people they're going to ship to Mars, it's not something that has, it's a complete unknown at this point. What's the survivability? And then let's talk about the third thing that I think is the large risk. These are risk factors that most people don't think about in terms of colonization, but the psychology. If you think about Columbus, he set off on ships. People would go out fishing for days or weeks even. So they're used to being on board a ship for long periods of time. And even more than the amount of time it would take him to get to the New World. He left with 3 ships and about 90 crew. And not all of them were very happy, and not all of them were volunteers. And for sure, not everybody came back. They had casualties, they lost ships, and it was an adventure and a half, right? And there's some things that are similar, and there's some things that are quite different. I think for Mars, you're going to have a lot of people that want to go and would be glad to volunteer. But once you start talking about the reality of that, how many people are actually qualified, or even, when they see the realities of moving to Mars or going to Mars for an extended stay, it becomes a whole different question. So I'm not sure you're going to get masses of people that are going to want to move to Mars. Also, another difference is if you're on a ship, if anybody's been on a ship for a while, you're cooped up with the same people on the same spot for quite a long period of time, and it becomes quite intense in terms of the interpersonal relationships. It's not something that is easy to deal with psychologically. So let's take a look at the current SpaceX ship that's going to take people to Mars. This is just an artist's rendering of what they think could happen. I brought this up just because the volume is correct. The amount of volume in this starship is roughly the same as the volume inside a super jumbo, like a 777. Of course, it's not configured in a long tube. It's more of a larger cylinder. And if you look in here, you can see there's seating areas. You can fit, let's say, 15, 20 people in a circle seated. There's cabin areas. You could have little cabins. And you can imagine that each one of these cabins, it's not a lot of room in there. It's very small. So let's say you put 20 people in this capsule. You're going to have all their food, water, clothing, everything on board for 300 days, 20 people. Now you can imagine you go into your room, hang out there for a little while, watch the same episode of, whatever your favorite Netflix show is. I mean, after like 4 days being in your room, and all of us under quarantine understand this distinctly, it sucks, right? Imagine 300 days where all you can do is go from this little cabin to sitting at one of your consoles to up here in the common area where everybody talks, eats, drinks food, stuff like that. I mean, there's not that many things to do. There's not a lot of places to go. There's not a lot of activity. And it's going to be a very unique set of people that are going to be able to withstand that kind of psychological pressure for that length of time. My guess with this volume of space, I'd probably be comfortable 10 people. I'd need my own room, and I'd need my own office, and I'd need my own bathroom. And yeah, I'd be on the ship that had the officers' quarters. And then I probably could do the 300 days, maybe. I'd be crazy, but if you put 30 people in here like this and stuff yourself in there, I don't know. You just snap. It only takes one person to snap when the whole thing goes funky. All right, let's move on to the next slide. I think that they will have a lot of games and activities. I mean, you'd have to schedule 300 days of activities to do. So you'd have to plan way, way ahead. And yes, I'd expect that gaming would be a large part of this, or running simulations, or stuff that keeps you mentally active and in the game, and allows you to still have some activity. Imagine there's nowhere to run in here. You're going to be on this little treadmill thing, strapped down like in the International Space Station. And there's no. Imagine the first guy who goes up and he's practicing his boxing or whatever, and starts sweating, and the whole capsule becomes stinky. I don't know. This just doesn't look fun to me. You're not going to have more than one or two actual bathroom facilities, and they will be just like the International Space Station, where you press and it's got positive suction, and it will be recycling everyone's bodily fluids as well. So you can't. This whole thing would have to be full of water to keep people alive for 300 days just for drinking. So yeah, everything gets recycled. And the last thing I want to bring up on this one is Crazy Elon's little speech, which is really good. So we'll talk about it a little bit after we start. So I'm just gonna press play, and it's a pretty short little video. So hopefully this works good. Hear it now?
Yes, I can, sir. Thank you.
Yes, sir.
Excellent. that's at 2022. He wants to send 2 cargo ships already. And then 2024, 2 cargo ships plus 2 crewed ships.
Earth-Mars synchronization happens roughly every 2 years. So every 2 years, there's an opportunity to fly to Mars. So then in 2024, we want to try to fly 4 ships, 2 of which would be crewed, and 2 of which two cargo and two crew. The goal of these initial missions is to find the best source of water. That's for the first mission, and then the second mission, the goal is to build the propellant plant. So we should, particularly with 6 ships, there have plenty of landed mass to construct the propellant depot, which will consist of a large array of solar panels, very large array, and then everything necessary to mine and refine water, and then draw the CO2 out of the atmosphere, and then create and store deep cryo CH4 and O2. Then build up the base, starting mostly with one ship, then multiple ships, then start building out the city, then making the city bigger, even bigger. You send the spaceship up to orbit, you retank it or refill it until it has full tanks, and it travels to Mars, lands on Mars. For Mars, you will need local propellant production, but Mars has a CO2 atmosphere and plenty of water ice. That gives you CO2 and H2O, so you can make, therefore, CH4 and O2 using the Sabatier process. Becoming a multi-planet species beats the hell out of being a single-planet species.
All right, so what do you think? We think Elon's crazy, or is this feasible? Given the things that we talked about, the 3 main hurdles that we talked about in this lecture, the radiation, microgravity, and psychologic part, let's do a Kahoot. Space itself. That's good. Nice. I like that. No Big Macs. That's going to be a problem on that for some people. Star Wars enemies. You mean the Empire is out there somewhere? Most of this revolves around food, it looks like. So everybody's worried about what to eat. All right. Very cool. All right. Let's see who we got. 3rd place. Barrack. 2nd place, Luke. And coming in hot, podium finish, Joker. Nice job. We got the Brainiacs filtering to the top, looks like. Some runners up. All right. If we do go to Mars, there's a problem about even moving around in the atmosphere because there's very little of it. So this has been a focus for a long time, and it's the motion on other bodies, other planetary bodies, or running around in the upper atmosphere of even Earth. So this is a quick lecture on those topics, and I think you'll find it quite interesting. So here's an example of a research vessel that's designed to fly in Mars' atmosphere, where the gravity is 40% of Earth's, but the atmosphere is very, very low density. So the aerodynamic profile in flying in very low density environments is roughly the same as trying to fly in the upper atmosphere of Earth. But there's also gravitational things. So you have less pull on the mass of your object, but you also have less atmosphere to lift. So there's a conflict there in terms of our standard flying around aerodynamics. The first high altitude flying was done by people in balloons because they didn't have the ability to fly high-performance jet aircraft in low atmospheric levels. The first flights were done via basically super enlarged weather balloons with these pressurized capsules. And one of these flights was of the Explorer, hit 72,000 feet. So these are the first people who were able to see the curvature of the Earth. So all the way up until 1935, no human had actually seen the actual curvature of the Earth. So that's pretty interesting. And if you want to look these guys up, their biographies are very interesting. Interesting guys. And this is an interesting time too. Just post-depression, 1935. So they were testing out a lot of different things. Here's another one of our favorite planes. Yeah, the U-2, and that's not a balloon, of course. So what allows the U-2 to fly at really high altitudes is these long, high aspect ratio wings. So it's much like a glider, and it has an internal jet engine, lots of fuel, and these really long glider-like wings. So it can cruise around at high altitude. And what's interesting is it's flying in a very interesting flight regime where it's very close to the stall speed. And we'll talk about that in a little bit right here. If we look at this chart, so this is altitude on the y-axis, and this is the airspeed on the x-axis. So as we're flying faster and faster and faster, we move this way. As we're going higher and higher and higher and higher, we move this way. Well, you'll notice that unless you're flying in a modern jet fighter or something, you're at the Mach limit. Now, some of you will know what the Mach limit is, and some of you may not, but this is where the speed of sound is in the density of air. So the air becomes less and less dense. As it becomes less and less dense, the speed of sound drops. It becomes lower and lower and lower and lower. There's a problem with transonic flight, so going faster than the speed of sound, you develop a pressure gradient at the leading edge of any object, and that pressure gradient is stark, and that's what's called the shock wave, or what we call when we hear something fly by, that is the sonic boom. It's creating an actual aerodynamic effect that's hard for a normally configured aircraft to actually fly in that. And this, if you're flying in a normal aircraft, is the stall limit for fairly high performance aircraft here, it looks like, because that's our Cessna stall limits are down here. So this would probably be for like the U-2. And then you have the Mach limit. So if we fly up in this high altitude range, we have this very limited flight regime. We can't go transonic, and we can't go into stalls, or else we lose control of the aircraft. So they call this the coffin corner, because when they were investigating high altitude flight, well, some of the test pilots unfortunately would end up in unrecoverable spins, and their aircraft would be demolished, and some of them lost their lives because of this. And that's why it's called the coffin corner. Hopefully that is a good explanation for you guys. Now, here's a reason why traditional aircraft don't do well in supersonic flight. We have an airfoil, which is designed to provide lift, and part of that design is angle of attack, and another part of that design is that the top surface has a longer run than the bottom surface. So the pressure differential favors higher pressure on the bottom and lower pressure on the top, providing a lift vector. When we start to get to Mach numbers near the limit, you get a shock wave developing where the air, remember, to make this lower pressure, we need to speed the air up. So the air has to go a little bit farther over the top, so it speeds up. So it turns into supersonic flow right here on top of this airfoil. And then that supersonic flow produces a shock wave. So the shock wave is bad. It causes all of the unstable air behind it, and this wing basically just stops to work. And if you increase that even more, then you get supersonic flow on the lower surface, supersonic flow on the upper surface, but you can tell that this is going to be a differential in pressure gradients that's extreme, and it's going to break this wing up. and that's called the Mach Tuck. And that's exactly what happened to this aircraft, which is one of my favorites. This is the first aircraft probably to survive almost supersonic flight, but it was susceptible to the Mach Tuck, and they noticed it in flight. But I love this video so much that I'm just going to show never get sick of that sound. Sorry, we had to digress for a minute because what a beautiful machine. So, yep, this is one of the first aircraft where actually the pilot could look out onto the wing surface and start to see that supersonic flow regime. You see, you know, like you can see contrails type of thing forming, foggish area, and you could see the actual shock developing on top of the wing surface. So this aircraft was one of the aircraft that they used that indicated that Mach Tuck. Whoops, missed that. So after we figured out jet engines and getting past into the supersonic flight regime, we made some really fascinating aircraft, and the SR-71 is one of my favorite, obviously. It's flown higher and faster than just about anything else. And in this shot right here is from 73,000 feet. I couldn't get a picture from the actual top end limit, but think about that, 85,000 feet. So that's when we're looking at that U2 coffin corner thing. So this broke way past that, and you're up into air that's so thin that the concept of regular aerodynamics don't exactly fit. So it's fantastic. And this thing is still running on these crazy engines that are just, they're like combination jet engine, ram air, and it's an amazing aircraft. I encourage anyone that doesn't know about it to go look it up. And yeah, we have to look at this too. Okay, so we don't have too much time. I can't sit here and just watch aircraft all the time, but that's a fantastic machine. So let's take a look at this limit here. Also about the SR-71, which is really interesting to me, that like it was designed to heat up. So on the ground, it would be leaking jet fuel because the panels of the plane itself had such big gaps that fuel would be leaking out of it. And then once it heats up, it seals itself up, which is quite interesting. Fascinating aircraft. So this one is showing thrust, power. These are kind of equivalent in sense. This is a propeller-driven aircraft. This is a jet aircraft. So you can see that there's a ratio between induced drag and parasitic drag. So you end up with your total drag in these red curves. And it's completely different between a jet plane and a propeller-driven plane. So propeller-driven plane becomes very high drag at a certain point, and it can't really transit even into the supersonic regime without severe drag problems. And you can notice over here, so if we go to 400 indicated that on this curve at 4,000, the drag for a propeller-driven plane is here, and the drag for a jet aircraft is here, which is a significant decrease in drag. So jet aircraft much more efficient at higher speeds. And that comes into play into this, which we're going to skip because we're not worried about mathematics today. But just note that lift is a squared function of velocity. The faster you go, the more lift you can get, the less you have to worry about having big fat wings with, thick cords. That's why a jet aircraft can have very, very, very thin wings, because lift is a squared function of velocity. The problem, though, is that with very, very thin wings, you have to be going quite fast, so landing and taking off are a little troublesome. But that's dealt with big flaps and stuff like that. Now let's talk about the frontiers of high altitude right now, currently, are all drones. We don't have human-powered craft that are flying up in the high altitudes. So here's a list of current drones that are either in research and development or actually being produced. Pretty cool. Some of these are really cool. You can go take a look at them. Some of these are very weird designs. They look very odd. The one we're going to look at right now, though, is just this Phantom Eye Boeing's. Looks like some kind of a whale. I'll have a quick look at it. Quick look.
It was only Phantom Eye's second takeoff, but it performed it as though it had done it 100 times before. After reaching its takeoff speed of nearly 60 knots, Phantom Eye lifted off from its ground cart and gracefully climbed to more than 8,000 feet to begin a 66-minute flight.
Seeing that bird lift off the cart like that was a sight to see.
Engineers and ground crew watched as Phantom Eye climbed to 5,000 feet, and then as it banked and soared to its cruising altitude over Edwards Air Force Base.
502, can you give us a wind check?
Powered by its two 150-horsepower liquid hydrogen engines, Phantom Eye's 150-foot wings glided the unmanned aircraft through California's high desert sky.
Wind 350 at 5.
All right. Just pause there because I think you get an idea of how cool these new aircraft are going to be. So this is going to probably a design like this, or some form of aircraft like this, is going to be replacing some of the other observing aircraft that we have even in the military fleet. So now we get back to the end. We're going all the way back to Mars. This funky little helicopter is actually now installed on the next rover mission to Mars, which is going to launch potentially sometime this year, barring any pandemic delays. So let's take a look at that. This is amazing technology. Remember, Mars has only 1% of the atmosphere of Earth, and they got a helicopter to work. Check that out. In that space, that room, that's actually drawn down to closer to vacuum, and that in that room is only 1%, or the equivalent of like 80,000 feet high altitude. So getting a helicopter to fly in that environment is just an amazing engineering feat. And there we go. So that concludes our flying high portion. I know we blasted through a little bit of it, but want to end on time. All right, well, I thank you all, and I'm going to leave this particular meeting, and I'm going to go jump on the simulator and fly, because none of us can fly except for me now. No, if you can come down to wing headquarters and you're a pilot, the Redbird is operational.